Morning everyone. So, we will start with the natural convection. So, it is basically a natural or free convection, they are same, and whatever convection we have studied till now, that is basically forced convection. Now, the major difference between the forced or free convection, this is also free, right. In forced convection, you will be forcing a fluid to flow past either a surface or through a conduit. So, you must be having an external agent which will be forcing the fluid to flow. Now, that external agent may be a compressor, may be a fan, okay, may be a blower. And in case of free convection, you do not have an external agent to force the fluid to flow. No external agent. In this case, in free convection, but there is a condition in free convection that there must be a density gradient present in your flow field in presence of a body force. A density gradient, and this density gradient is generated due to the temperature difference, and as temperature increases, most of the fluids, almost all the fluids, they will be having lower density. Present against a body force. But again, there will be certain condition when even if there is a density gradient present in case of with a body force, you may not have a free convection. Okay. Now, this density gradient is generated due to temperature difference. Okay. This temperature difference and density gradient will give rise to a buoyant force. Now, when this buoyant force exceeds the viscous forces, then there will be setup of natural convection currents. If it exceeds viscous forces, then you will be getting a free or natural convection. Naturally, the heat transfer in a forced convection will be much higher compared to natural convection, because here in natural convection the fluid materials physically will be carrying out heat, will be carrying heat along with them from one station to another station. So, in natural convection you will be having less heat transfer compared to forced convection, and of course, the heat transfer coefficient in natural convection will be order of magnitude less compared to the heat transfer coefficient in case of forced convection. Okay. Now, consider two plates at two different temperatures, T1 and T2, and let us say the direction x is pointing downwards in the same direction of gravity force. Okay. And temperature difference, temperature profile existing between the two plates, something like this, T2 is greater than T1. Okay. Since density is inversely proportional to temperature, so the density profile will look something like this, rho 1 and this is rho 2. T1 is less, so rho 1 is high. Now, what happens? The fluid adjacent to the top plate will be heated up. Okay, they will be the fluid adjacent to the bottom plate, they will be heated up and they will become lighter. So, they will try to move up. If that buoyant force, what will be the density difference, what will be acting over them, if that exceeds the viscous forces, they will simply move up. And at the in the presence of this temperature, they will be again cool down. Okay. So, and they will become heavier. So, there will be a setup of current, flow of materials, okay, and this will cause, and this is the natural convection current, is known as the natural convection current. And physically the heat is transported from one place to one station, from one station to other station. So, basically the heavier fluid comes down from top and gets heated up in the bottom plate, and the resultant buoyant force, this buoyant spelling may be wrong, okay. Buoyant force, it exceeds the viscous forces, they move up, cool down, density increases, becomes heavier, comes down. So, forms a heat current or heat flow, or causing a natural convection current. The situation will be entirely different if you have a just opposite scenario. Suppose you have two plates like this, and the temperature, and there will be, you will be having the x direction down in the same direction with the gravity, and you have a temperature of the top plate and you have the temperature of the bottom plate T1 and T2, and T2 is greater than T1. Now, the other way around, right? T1 is greater than T2. This T1 is greater than T2. Okay, and the density gradient will look something like this. The lower plate will be the fluid adjacent to the lower plate, it will be heavier and it will be staying there, and temperature is also less. So, there will be no setup of convection current. So, in this case, even if this T1 is greater than T2, there will be transfer of heat from bottom plate to the top plate, but not by natural convection, because you cannot set up a convection current here. Once again, this temperature, let us say we have the same scenario, if the top plate is having a temperature higher compared to the bottom plate. Okay. The fluid adjacent to the top plate will become lighter. So, they will stick to the top plate, they will try to move up if it is, so they will stick to the top plate, and the fluid at the bottom plate, they will become heavier because they are at the lower temperature. So, they will remain, since they are heavier in the same direction of gravity, they will be remain in the bottom plate. So, there is no way of to overcome viscous forces, because there is no upward force, there is no buoyant force acting on them. So, you will not be having a creation of physical movement of fluid material. Okay. So, there is no chance of getting a convection current here, but since this temperature of the top plate is higher than the temperature of the bottom plate, there will be heat flow. So, the heat will be always flowing from higher temperature to lower temperature. So, there will be heat flow in this case, but that heat flow is not due to natural convection, that heat flow will be simply due to conduction. Okay. Since T1 is greater than T2, so there will be a heat flow from top to bottom plate, but the mode is simply the conduction, not convection. Okay. Now, the plates, maybe in a practical problem, these will be maybe a simple plate, or maybe a cylinder, maybe a sphere placed horizontally, vertically, whatever position may be. Let us look into how to develop the heat transfer coefficient for such a system. Boundary layer development on a heated vertical plate, and we will see how to find out the heat transfer coefficient in such case, and it is a case of constant wall temperature. There will be sort of boundary layer. Okay, I will draw the diagram, then that will be easier. Suppose you have a vertical plate, something like this, and this you have temperature Ts, and that is uniform. Okay, and you will be having a stationary medium outside with temperature T infinity and density rho infinity. Density of the fluid will be a strong function of temperature, and density and temperature of the stationary medium will be T infinity and rho infinity. Let us say x is in this direction vertically up with a velocity component u, and y is in the direction that is normal to the plate with a velocity component v. Okay. Now, there will be development sort of boundary layer development over this. Now, temperature, velocity at the wall, all the velocity components at the wall will be vanished because of the no slip boundary condition. There will be some kind of the temperature will be Ts, and at the edge of this sort of boundary layer there will be formation of boundary layer. That means due to convection currents there will be existing a temperature difference, because that is why the convection will occur, and that temperature difference will be something like this, that terminal at the plate surface at y equal to 0 and y equal to some kind of delta, okay, where you will be having T infinity, right, and velocity will be is equal to 0 at the edge of the boundary layer at all points. Because what is the boundary layer? Boundary is basically the the surface, right, or the trajectory where the velocity component will be 99% of the free stream velocity value. Here free stream velocity value is 0, because this is stationary medium. So, velocity values of all the two components will be equal to 0 at the edge of the boundary layer, and velocity will be 0 somewhere at the surface of the plate because of no slip condition. Velocity is 0 at the edge of boundary layer, but there will be velocity component existing here within this region. So, velocity component will look something like this. It reaches a maxima, then again it will drop down. It starts from 0, reaches a maxima somewhere in between, it may be half, maybe 1/3, that we will see later on, and it will be again comes down to 0 velocity at this. And temperature profile will be falling something like this. It becomes T infinity at the edge of the boundary layer starting from Ts at the wall. Okay. So, basically fluid close to the wall will be heated up, Ts is greater than T infinity. Okay. Fluid present close to the wall, close to the subplate, it will be heated up, and there will be buoyant and becomes less dense, and there will be buoyant force acting on it. It most probably it will overcome the viscous forces, it will move up. So, there will be kind of boundary layer. It is not exactly boundary layer, but it is sort of boundary layer that will be existing close to the plate, and we assume that thermal and velocity boundary layer will coexist in this case. This is simply an assumption, there is absolutely no proof. Coexist, or the better word is coincide. They will coincide. Okay, it is not a case that velocity boundary layer is within the thermal boundary layer or thermal boundary layer is within the velocity boundary layer. It is assumed that both the boundary layers will coincide. Okay, so since fluid will move up, it will entrain some fluid element just outside the boundary layer. Why it will entrain? Because if you put the equation of continuity and evaluate at the edge of the boundary layer, the velocity component will not be equal to 0. There will be some kind of velocity that will be present there. Del v del y will be present. It will be very, very small. Because of that some kind of entrainment will cause from the atmosphere, and again that will move up, and it will set up a natural convection current. So, the governing equations that we will be writing. One will be x momentum u del u del x plus v del u del y is equal to minus 1 by rho del p del x minus g plus nu del square u del y square, and we consider the flow within this region is laminar.
So here we are taking velocity and thermal boundary layer
Coincide.
So why
Actually, the definition of boundary layer, what we have in case of forced convection, the fluid is flowing over a plate. It is the scenario is not like that. Okay, so in that case, there is simultaneous development of velocity boundary layers, thermal boundary layer at the same time, right? And depending on the Prandtl number, etc., fluid properties, you will be having whether the velocity boundary is within or outside. But in the case of natural convection, you do not have such kind of thing. Okay, there will be velocity existing, but the velocity will be equal to 0 somewhere in the y direction away from the plate. There will be some kind of temperature profile existing close to the plate, and it will be equal to T infinity somewhere. And this is not exactly boundary layer. Okay, the way that we define the boundary layer, what it is some kind of boundary layer, and it is a sheer assumption that velocity and thermal boundary layer will coexisting or coinciding. So otherwise, the mathematical analysis becomes very difficult. That may be, to my estimation, that is the most crucial thing. That you must have seen that whenever we are solving the boundary layer problems, the condition at the y direction, sometimes we put y equal to infinity, sometimes we put y equal to delta, right? Although I said previously also, all the boundary layer thicknesses will be pretty small, whether it will be velocity boundary layer, not the velocity boundary layer, there is a concentration on thermal boundary layer, but heat or mass transfer will be occurring within that small thickness of boundary layer. So any distance away from the boundary layer, you will be having the concentration will be equal to feed stream concentration, or temperature will be feed stream temperature. Now, suppose this thickness is in the order of 10 to the minus 6 meter, let us say, and in your actual scale it is centimeter, millimeter. So at least 3 or 5 order of magnitude, 3 to 6 order of magnitude higher compared to the actual boundary layer formation. But whatever heat transfer, mass transfer occurs, that occurs within that small thickness. Now, what is the boundary condition you will be putting? So any distance in realistic sense will be equal to infinity compared to the boundary layer thickness, or you can, if you would like to do a more rigorous solution, y equal to delta. So it is basically mathematical convenience of the situation, then you set the governing equation, put the boundary conditions.
So if you take mercury as the stationary fluid, so then the
mercury is very dense, so you won't be having natural convection in that case. Its density is very high, right? What is the density of mercury? It is 136 times higher the water density at normal temperature.
So if the temperature difference is very high, we will have no natural.
I don't think you will be having natural convection at all in mercury. In fact, you require very high temperature difference to have natural convection in water. All these natural convections are basically for the gaseous fluids. You see, in all the problems in your book, natural convection is very rare in case of liquids because of their high density. Okay. Since we are considering it is a boundary layer, that V component will be extremely small compared to U component. Okay. So in Y momentum, when you write down the Y momentum equation, then all the V contouring terms will vanish, okay, and the only term will be remaining is del P del Y is equal to 0. If you remember the boundary layer analysis, fine, then you will be having, if del P del Y equal to 0, you remember this one, right? If it is a flow over a flat plate, this is x direction, this is y direction, you write x component equation of motion. You do not write y component equation of motion, because the velocity v is order of magnitude less compared to velocity u. So all the components, all the terms containing v, they will be cancelled, they will be negligibly small apart from the del P del Y. So you come to a conclusion that del P del Y equal to 0 in that case. Similarly, here also you will be having del P del Y equal to 0, that means P is a sole function of x or it is a constant. Now, you evaluate x momentum at the edge of boundary layer, right. What you will get? At the edge of boundary layer, U is not there present, so that will go off. U is go off, so del U del Y will be off. U is basically U equal to 0. Is the surrounding air is in stationary condition. So this term will also off. So you will be getting 1 by rho infinity del P del S equal to minus G. Rho will be replaced by rho infinity at the edge of the boundary layer, right. Now, since your del P del Y is equal to 0 for all x and y that you have obtained from the y component equation of motion, and del P del x equal to minus rho infinity G for all x and y. Now, you can safely replace del P, you can write down your x momentum equation. X momentum equation takes this form: u del U del x plus v del U del y is equal to G by rho, rho infinity minus rho plus.
Del U by del Y, so must be very less, not equal to 0. Otherwise,
No, del U del y will be comparable to these two terms will be comparable, because you will be having whatever value itself is very small and delta y is also small. So the ratio will be in order of 1. If you do an order of magnitude, if it is just exactly the boundary analysis whatever we have done for a flat flow over a flat plate. Okay. This term comes in case of a flow over a flat plate, that term would have been exactly equal to 0, because the density was fixed in case of a flow over a flat plate. So this term will appear and it represents some kind of density gradient, and which will be giving rise to a buoyant force here. So this represents a buoyant force giving rise to a natural convection current, and rho is a function of temperature. We define volumetric thermal coefficient beta as beta equal to minus 1 by rho del T at constant pressure, right. And this can be written as rho infinity minus rho T infinity by minus T, and it is we assume that this gradient is linear over the temperature difference T and T infinity. Then only you can write this equation, and beta is constant. Over this temperature range. Okay. Then you can replace rho infinity minus rho by beta times rho into T infinity minus T. Okay. So your x momentum equation takes this, so rho infinity minus rho will be can be approximated as by rho beta T minus T infinity. This is only an approximation. Again you are having an approximation here. So your x momentum takes this form: u del U del x plus v del U del y equal to g beta T minus T infinity plus nu del square U del y square. Now see, in case of natural convection, you will be having an extra term which is basically buoyant force term, which will be a function of density, which is in turn a function of temperature. By using this approximation, you can express that function of temperature as a linear function, as an explicit function with temperature. The variation of density difference can be related explicitly with temperature. So you cannot solve this equation independently. This is a coupled equation, This is a coupled x momentum equation with the energy equation because of this term. So, obviously, this will be x momentum. You have already consumed y momentum to get this one. Now, you have then equation of continuity del u del x is equal plus del v del y is equal to 0, and the third equation is energy conservation equation. That is u del t del x plus v del t del y is equal to alpha del square t del y square. That is the energy conservation equation. So, now these three equations have to be solved in order to get t as a function of x and y. Then you have to evaluate del t del y at y equal to 0, right. Once you evaluate del t del y at y equal to 0, then you defined your heat transfer coefficient T vol minus T infinity equal to minus k del t del y at y equal to 0. Now, numerically you will be getting a value of del t del y at y equal to 0 for all x. So, you will be getting a local value, local heat transfer coefficient, and finally, you will be getting a numerical value of average heat transfer coefficient by simply doing a length averaging of this. Now, there are some kind of analytical solutions are present and with certain approximation. The first one is integral method, second one is similarity solution. In integral method, you assume a profile of velocity, you assume a profile of temperature, substitute in the governing equation and integrate across the boundary layer thickness. In this case, both the boundary layer thickness is equal to delta, let us say, and solve that and find out the solution. The second one is similarity solution, and I will just give a brief outline of the similarity solution because the detailed derivation of similarity solution is probably out of the scope of this course. That will be can be a material for any advanced course. So, just some idea of how this heat transfer coefficient varies with distance and how what is the form of heat transfer coefficient with the dimensionless numbers, because that is the most important thing, because we are dealing with the mostly all the forced convection. We have said that from theoretical basis, even the theory is based on some semi empirical correlations like Prandtl's mixing etc. So, by some kind of semi analytical method, you can proceed up to some time, up to some step, and can get a form of variation of either friction factor or Nusselt number or Sherwood number, the variation of those numbers with respect to dimensionless numbers like Reynolds number, Prandtl number or Schmidt number in case of mass transfer. Now, the form of the variation is important, whether your Nusselt number is varying Prandtl raised to 1/3 or Reynolds raised to 0.5 or 0.33, that is important. That variation can be obtained, that the functional variations of this dimensionless number with these dependent variables, friction factor, heat transfer coefficient and mass transfer coefficient is important. Once you get the functional variation, now what will be the coefficients etc., what will be, that will be coming empirical coefficient in front of that, those relations, those will be system specific and fluid specific. So, all the forced convection cases you will be using most probably the correlations, but the form of correlations can be derived from the fundamentals. It is only that, but in case of laminar flow, you can get exactly the analytical solution and can get exact formulation for a heat transfer coefficient or mass transfer coefficient, variation of those terms, quantities in terms of your dimensionless number, Reynolds number, Prandtl number, Schmidt number, etc. So, here also you will be getting some kind of analysis to get actually the form of variation of this Nusselt number with there will be a term coming, new dimensionless number coming in the case of natural convection, that is known as Grashof number. Okay. So, and Prandtl number etc. So, we will get that form at least. So, for that you have to make the governing equation non-dimensionless. Dimensionless, you have to make them non-dimensional form. So, in order to obtain the non-dimensional forms, you have to define the non-dimensional quantities. X star will be made non-dimensional against the length L of the length of the plate. Since you have the length only, so y star is y by L U star is U by U naught. Again, you do not know what this U naught is, because there is no free, external surrounding is at stationary condition. Okay, some kind of velocity, let us say, that we do not know, and it is very risky to make some dependent variable against some unknown variable. Okay, for the time being, we consider that U0 is some kind of velocity which is used to make the velocity component to be non-dimensional. Again, V star is V by U0. Now, T star is made non-dimensional by T minus T infinity by Ts by T infinity, and L is the characteristic length. Characteristic length is basically length of the plate. U0 is arbitrary velocity, reference velocity. So, in terms of these non-dimensional quantities, you will be having U star del x star plus V star del U star del y star is equal to G beta Ts minus T infinity L U0 square T star plus 1 over REL del square U star del y star square. Okay. This is the Reynolds number based on length L, and we will be having a new non-dimensional number in this form, and your energy equation becomes U star del T star del x star plus V star del T star del y star is equal to 1 over REL PR del square T star del y star square. Okay. These are the forms of the non-dimensional governing equations, the x component equation of motion and energy equation. Now, again, the reference velocity is unknown and it is very inconvenient, right. So, and your Reynolds number is defined on this U0 L by nu. That is the way the Reynolds number is defined in terms of reference velocity, and it is based on the length L. Now, we define a new number known as Grashof number. It is defined like this: G beta Ts minus T infinity L by U0 square U0 L by nu whole square. What is this? This is the Reynolds number, and this is the non-dimensional number that was appearing in your equation of motion. Okay. Now, by definition of this Grashof number, you can do away with the unknown reference velocity u naught. That is the idea of defining this number, because ultimately you will be what is Grashof number? Grashof number physically means buoyancy force divided by viscous forces. Okay. And it becomes G beta Ts minus T infinity L cube divided by nu square. This u0 will be cancelled out. So that is true. If whether the depending on the magnitude of Grashof number, you can say my buoyant force is dominant, my viscous force is dominant. If my viscous force is dominant, then I will not be having any natural convection. If my buoyant force is dominant, then I will be having natural convection. So all this conclusion you can draw just by looking into the Grashof number. If both are more or less in equal magnitude, then you can say both both free and forced convection can be of importance. Now, since the number is a characteristic number for the case of natural convection, all your correlations for heat transfer coefficient or Nusselt number relations will be a function of Grashof number. So, suppose you like to compute the heat transfer coefficient, you know all the parameters, temperature specification, etc. So, you would like to compute the Grashof number, right. So, now in this form all the quantities are known. So, that is the reason why Grashof number is defined in this way, the quantity times Reynolds number square, so that you can do away with or you eliminate the unknown reference velocity u naught. Defined in this way, velocity u naught. So, you can expect your Nusselt number will be a function of Reynolds number, Grashof number and Prandtl number. Okay. Now, you have to look into this quantity GRL divided by REL square. Now, this REL will be based on if there is some kind of flow present in your situation, in your system. Now, if it is a stationary fluid, this Reynolds number will not exist. There exists only the Grashof number. Okay. But if there is some kind of flow existing in your system, there may be natural convection as well, even in presence in forced convection. Forced convection may be 100 times order in magnitude higher compared to natural convection. So, the amount of heat that will be transferred by natural convection will be, if it is 1, then in case of forced convection it will be 100. So, it will be totally 101. So, it does not matter. Even in some case they will be equal in magnitude. So, if there is some kind of flow existing in your system, you can define a Reynolds number based on that flow, because the flow velocity is known in that case, and you can compute, you have to compute this number, this ratio, Grashof number divided by Reynolds number square. Okay. If this will be, this quantity is in the order of 1, then both natural and forced convection are equally important. Okay.
Sir, in that case, U naught will be U infinity.
In this case, yes, if it is a just a flow over a flat plate, then it will be U infinity, because that is the only velocity that is known to you, right. The way you are defining you are calculating the heat transfer coefficient for the flow over a flat plate, what is the reference velocity you take to define the Reynolds number, that is U infinity, it will be U infinity in that case. So, what my intention is, if there is a U infinity present, depending on its value, this ratio will be greater than 1, less than 1 or roughly equal to 1.
In case of a stationary medium,
Then there is no question of forced convection, there is only natural convection, right. So, if there is a flow over a flat plate or in a conduit, so you can compute this number and come to a conclusion which will be the dominant mode of heat transfer, natural or forced. If this ratio is roughly equal to 1, then both modes are equally important. Then free convection is small, right. It is mostly natural convection. This small means this Reynolds number, this viscous force will be very high. Okay. So, free convection is very, very small, and what you can expect, your Nusselt number will be a function of Reynolds and Prandtl, like all the correlations of Nusselt number you had previously. If it is other way around, then you will be having this, then forced convection effects are small. And you can expect your Nusselt number will be function of Grashof number and Prandtl number. Okay. Fine. All these conclusions you can draw just by putting the numbers, the non-dimensional numbers, and which mode of convection will be dominant. Now, let us come down to the solution. Again, I will tell you just this solution. I am not going into detail of this similarity solution of your governing equation. Now, let us, before going to the solution, you have to fix up your boundary conditions. At y equal to 0, u is equal to v is equal to 0 because of no slip. T is equal to Ts. At y equal to infinity, that means the same condition is your at the edge of boundary layer onwards, u is equal to 0, stationary media, and t is equal to T infinity. Okay.
So UV both at 0 in the
The medium is stationary. Its resultant velocity is 0 at any point If it is a two-dimensional flow field, what is the resultant velocity? Under root Vx square plus Vy square. That means both the components have to be equal to 0. At the edge of the boundary layer, velocity component of y exists, but it will be very small. Because of that, entrainment occurs. Otherwise, it will be very small. Okay. It is basically mass conservation. Okay. There is a plate, and the material is heated up. It is going up. The fluid particle will be heated up and it will be going up. But there has to be mass conservation locally. At every point there will be mass conservation. Where from it will be coming? It will be coming from the outside because of entrainment in this direction. Okay. So at the edge of boundary, so boundary will be some kind of imaginary trajectory where the velocity of y component will be, it will exist to induce the entrainment, but that magnitude will be very small if you really compute. Similarity parameter. Now, I think we have already decided previously how to determine the similarity parameter in case you have a self-similar profiles. Okay. Now, I am not going into detail how to determine similarity parameter in this case. The similarity parameter will take this form y by x, Grashof number based on x, not L, divided by 4 raised to the power 1 by 4. Okay. And the velocity component in terms of stream function is defined as psi xy f of eta. Again, I am not going into detailed derivation because my intention is to show how the Nusselt number varies with the Grashof number in its functional form, raised to the power what. But all these can be derived. Okay. You can look at an advanced book in Case and Crawford or some advanced book, all the derivations are there. So, we define u as del psi del y and v as minus del psi del x. Okay. And we define, so what is and f is a sole function of similarity parameter eta. Okay. Now, what you have to do, you have to get u as a function of del psi del y. This can be represented as del psi del eta del y. Okay, del eta del y can be evaluated from this, and del psi del y can be del psi del eta can be evaluated from this. Okay, in this way you will be getting f dash eta, that will be df d eta only, not the partial derivative, because we have assumed that f is a sole function of eta. So you have to get u as del psi del y, and in terms of eta later on by the chain rule of differentiation. Similarly, v can be evaluated in terms of eta only by the chain rule of differentiation, minus del psi del x minus del psi del eta del x. And you have to evaluate all the partial derivatives in terms of eta only and substitute in a governing equation. Now, if you do that, from momentum equation, you will be getting f triple prime. This is basically d cube f d eta cube, 3f f double prime minus 2f prime square plus T star is equal to 0, and energy equation will be coming as T star double prime plus 3 Prandtl number f T star prime is equal to 0, subject to eta equal to 0. Eta equal to 0 means at y equal to 0, right. F is equal to f prime is equal to 0 and T star equal to 1. Okay. At eta equal to infinity, you will be having f prime equal to 0 and T star equal to 0. You can derive all these equations if you put the partial derivatives in the governing equation. Now, what you have done, you have boiled down your partial differential equation into an ordinary differential equation, maybe of higher orders. Now, Nusselt number, the local Nusselt number can be computed as Hx by k to Qs double prime Ts minus T infinity. Okay. We put the derivation of the definition of heat transfer coefficient here. So, basically what you have to do, you have to evaluate minus k del T del y at y equal to 0. Okay. Now, minus k del T del y in terms of eta, it becomes minus k by x Ts minus T infinity local Grashof number raised to the power 1 by 4 dt star dx dt star d eta at eta equal to 0. These can be written in terms of eta like whatever we have done previously, and that will be the final form of heat flux at the wall. Basically, you will be evaluating del T del y in terms of del T del eta, that you are writing only. So, your local Nusselt number will be in the form of Grashof raised to the power 1 by 4 dt star d eta equal to 0, and these will be a function of Prandtl number, because if you remember your energy equation, in your energy equation you will be having a parameter Prandtl number coming. Okay. Now, you are evaluating T star as a function of eta and evaluating that T star dt star d eta at eta equal to 0. So, it will be remaining, so this quantity will be a function of Prandtl number only, parameters only. The parameter is Prandtl number in this particular case. Now, this can be written as minus grx by 4 raised to the power 1 upon 4 g of Prior. Numerically, you evaluate this derivative, this derivative dt star d eta for various Prandtl number and plot. That can be done because you have the whole solution in front of you for a particular Prandtl number, because you can solve a coupled ordinary differential equation for one value of parameter. Now, you just change the parameter Prandtl number and you will be getting a set of these derivatives and then plot. And then fit a some kind of curve and get that relation of this derivative with respect to that parameter, and this becomes 0.75 Prandtl raised to the power half 0.609 plus 1.22 Prandtl to the power half plus 1.238 Prandtl, the whole thing raised to the power 1 upon 4. This is basically a empirical fitting to the numerical results, and since this is done theoretically by varying different Prandtl's number, of course, this relationship is valid for a range of Prandtl number 0 to infinity. You can put a very low value of Prandtl number, can put very high value of Prandtl number. So, your Grashof number now becomes G beta delta t by nu square x cube. That is the definition of Grashof number with respect to x. If it is Grashof number with respect to L, then this x would have been replaced by the length L. So, now you are probably in a position to find out what is the local heat transfer coefficient, because this will be a function of x, or this will be x to the power 3 by 4. This local Nusselt number will be proportional to x to the power 3 by 4, right? And you can have the length average heat transfer coefficient of Nusselt number. Please do the intermediate steps, and finally, the length average Nusselt number or average Nusselt number will be in this form. So, you have to, so for a case of natural convection in a vertical plate, what you have to, in order to estimate how much heat has been transferred by natural convection, what you have to compute, you have to first compute whether how much is Grashof number, length average Grashof number, and you know this value GPR by that correlation. So, you evaluate all the thermophysical properties at a at an average temperature. It is called a film temperature. It is the arithmetic average of surface temperature and bulk temperature. That is the free stream temperature T infinity. Now, evaluate GPR, evaluate Grashof number, because you have in the definition of Grashof number you do not have the reference velocity, because you have done away with that. You know all the other variables, and compute and find out the average heat transfer coefficient, and get the what is the amount of heat that has been transferred in what, that will be area, what is the area, length multiplied by the width you have, that will be specified, multiplied by the heat transfer coefficient, average heat transfer coefficient, and Ts minus T infinity, that will be the total amount of heat that has been transferred in order by natural convection in energy per unit time. Okay. Now, again you will be having various situations like whether the plate is horizontal, whether it is a case of constant wall temperature, constant wall flux, whether it is a, instead of plate you are having cylinder or a sphere. Okay. So, again there are different formulations for those, but mostly once you know the form of variation of Nusselt number with the Grashof number and Prandtl number, the dominant the non-dimensional numbers that are characteristic for your system, then you will be basically taking recourse to the various correlations, and you should know how these correlations should be used to attempt a particular for solution of a particular problem. So, in the next class whatever we will be doing, we will be looking into those specialized cases and various correlations of estimating the heat transfer coefficient and how to apply them in certain examples. Okay. Thank you very much.